Guys, welcome back to my channel. I think that you saw my last video, and now we are going to learn about the irrational numbers. So to understand the irrational number, first I'm going to explain you about the Pythagoras theorem. So for the Pythagoras theorem, we need a right angle triangle. As you can see, it is a right angle triangle, and B is 90 degree in this triangle. And here you can see B is 90 degree, AB is the perpendicular, and BC is the base, and AC is the hypotenuse. As you can see, it's hypotenuse, it's base, and it's the perpendicular. So according to the Pythagoras theorem, uh, uh, hypotenuse square means AC square equals perpendicular square means AB square plus base square. Here base is BC, so BC square. Or you can simply write AC equals under root AB square plus BC square. It means that hypotenuse equals under root perpendicular square added to base square. So it is the Pythagoras theorem, and by this theorem Pythagoras proved that there are another set of numbers which are irrational, which neither come in the category of rational numbers or integers, whole numbers, and natural numbers. So this is the fifth set of numbers which is called as irrational numbers, and there are many irrational numbers we come across daily, like under root 2, pi, under root 3, under root 5, under root 7. These all are irrational numbers, as after decimal expansion there are many after decimal expansion they never end, or some of the numbers continuously repeat, like when we have 1 by 3 and its decimal expansion is 0.33333, and here 3 never ends. The bar above the 3 is that 3 is occurring many times. So like this is an example of irrational number, like 0.33. So these are many examples of irrational numbers. So now I will explain you how to find these irrational numbers on number line. So guys, now we are going to find the value of root 2 on number line. So now draw a line of 4 centimeters and mark the numbers on it. As you can see here, 0, -1, -2, +1, +2, +3, +4. As according to Pythagoras theorem, under root 2 equals under root 1 square plus 1 square. This is base, and this is our perpendicular. This is our base, and this is our perpendicular. So therefore we will draw a 1 centimeter base first. So from 0 till 1, this is our 1 centimeter. I will name this point as O and this point as A, and then I will at the 90 degree I will make a 1 centimeter line from point A, and here comes my 1 centimeter line, and this is also my 1 centimeter, and I will join OA, and I will join this point, and this gives me B, point B. So now take a protractor, point it on A, and the pencil should be on B. So take this as the radius and draw an arc on the number line. The point where it cuts the number line is the value of root 2 on number line. So like this we can find the value of under root 2 in the number line. Now let's find the value of under root 3 on number line. So as we know, under root 3 equals under root 2 square plus 1 square. That gives us under root 3. So according to this, so we will again draw a number line. So as you can see, I already have a number line. This is root 2. So I already have a number line, and this is my under root 2 centimeter, and from here at an angle of 90 degree I will draw a line of 1 centimeter. So this is my 90 degree, and I am drawing a line of 1 centimeter. I will join that line to O and name this as C, and now take the protractor, take the compass again, and this time OC will be our radius, and cut the number line with that. The point where it cuts the number line is the value of root 3. So hence we found the value of root 3 like this. Now let's go to the exercise. So as you can see, the first question says, state whether the following statements are true or false. Justify your answer. So the part 1, every rational number is a real number. As you know, in the real numbers are many, 0, 1, minus 1, 3 by 2, minus 3 by 2, plus 3 by 2. So real number consists of each and every number. So therefore every rational number is a real number, as the set of real number consists all the numbers. So in all the numbers, irrational numbers, rational numbers, whole numbers and integer, all are included. So therefore the first statement is correct and it is true. Now the second statement comes, every point on the number line is of the form under root m, where m is a natural number. So according to this, it says every number in the under root form is present, is a natural, where m is a natural number. As you all know that in the when there is under root quantity, we always get a positive number, and m is a natural number, so we can only place the natural positive numbers. So there is no chance of getting a negative number, but the number line consists of the negative numbers too. So therefore the statement is false. Now first question, third part, every real number is an irrational number. So as you all know, real number is the set of integers, rational numbers, whole numbers, natural numbers and irrational numbers. But the statement says that only irrational numbers are real numbers. So therefore the statement is wrong. You can clearly see that 0 is a whole number and is a real number too, but it is not an irrational number. So therefore the statement is wrong. Now let's go to question number 2. Are the square roots of all positive integers irrational? If not, give an example of the square root of the number that is a rational number. The question states that under root m is irrational for all the values of m. So is that true or false? So it is false. As you know, under root 4 is 2, which is a rational number and it is not an irrational number. Under root 2 is an irrational number and under root 4 equals 2, which is an rational number. So this is the example, and the reason is no, as under root 4 is a rational number. So this was the explanation for that. And now let's go to question number 3. Show how under root 5 can be represented on the number line. So according to Pythagoras theorem, under root 5 equals 2 square plus 1 square. Here 2 is the base and 1 is the perpendicular. So again make a line of the length which you require, and mark the points 0, 1, 2, 3, minus 1, minus 2, minus 3, 0, 1, minus 1, minus 2, minus 3, plus 1, plus 2, plus 3, and so on. So and as we know here, we have base of 2 centimeter. So I join 0 from 0 to 2, and I take 0 as O and 2 as A. And now at an angle of 90 degree, I draw a line of 1 centimeter, as my perpendicular is 1 centimeter. So here comes my 1 centimeter line, and now I will join O to that point, and I will name this point as B. So as you can see, OA is 2 centimeter and AB is 1 centimeter. So according to Pythagoras theorem, base square plus perpendicular square gives hypotenuse square. So our hypotenuse is root 5. This is under root 5. So now we will again take a compass, place one end at O and one end at B, and again we will cut the number line at the point. So at the point where the number this cuts the number line is the value of root 5. So hence we found the value of root 5. So guys, here we have completed exercise 1.2, and now we are heading towards the exercise 1.3, and here it starts. So here the stadium. So the first topic is real numbers and their decimal expansion. As we know, when we divide 1 by 3, we get so like this 1, 0, 0 1, 3, 0.3, and 3 3s are 9, which gives the remainder 1, and again 0. So 3 3s are 9, and again 1. So this keeps on repeating, and the remainder never gets 0 in this case. And now let's take another example like 7 by 8. When we divide 8 like this, so 7 is smaller than 8, so we will take a decimal point, so 70. The closest number to 70 is 64. 8 8s are 64. So 70 minus 64 gives us the remainder 6, and again we place a 0 here. So the nearest number to 60 in the 8 table is 56, which comes at the 7. 8 7s are 56, and which gives us the remainder of 4. Again we place a 0, and the closest number to 40 is 40, as 8 5s are 40. So this gives us 40, and we get a remainder of 0.875 in this case, and 0.3 bar in this case. So bar represents that many numbers. If a bar is placed above any number, it means that the number is repeating many times and the number will never end. So like this, now I'm going to tell you about two types of number. This is a non-terminating decimal expansion, and this is the terminating decimal expansion. This is the non-terminating decimal expansion. This is a terminating decimal expansion, as after some time the numbers have stopped and the numbers have end, but here the number doesn't end. So this is a non-terminating decimal expansion, and this is terminating decimal expansion. Here the numbers never end. They continuously repeat, or sometimes they do not repeat, but the number never ends. Here after a finite time the number ends. So this is terminating, this is non-terminating. Now I will explain you another term, which is recurring. It means that the decimal expansion is repeating continuously, like 0.1212121212. This is the type of recurring point decimal expansion. And now let's take another example of non-recurring. For example, 0.12122122122. So this is a non-terminating decimal expansion, as none of the digit is repeating after a particular span of time. So commonly we will find non-terminating and non-recurring decimal expansions, and the value of non-recurring is, the pi also comes under this category, under root 2 also comes under this category. So these are the numbers which are non-terminating and non-recurring. So now let's find out some of the number. Can we write all the numbers in the p by q form? So first let's take an example like 3.142678. This is the number, and we have to write this number in the p by q form. So to write this number in the p by q form, we take as this is an non-terminating, this is the terminating and non-recurring decimal point. So very simple. We write the number same, and how many numbers are, let's count how many numbers are there after decimal point. 1 2 3 4 5 6. We add that many zeros after 1 in the denominator, and this is the p by q form of this number. As this was a terminating decimal expansion, so therefore we were able to do this. Now let's take an example of non-terminating decimal expansions, like 0.3 bar, and we have to write this in the p by q form. So as we know, let us assume that x equals 0.33333. As I already told you, bar represents that the number is repeating continuously. So now let's multiply both sides by 10, which gives, and let's assume this as equation 1. So 10x equals 3.333333, and so on. Now let's subtract both the numbers. We get 10x minus x equals 3.3333 minus 0.333. As both the numbers go till infinity, so we can cancel point numbers after the decimal expansion from both sides. Like after this we will get 10x minus x will be equals to 9x, and 3.33 minus 0.33 will give us 3. So x will be equals 3 by 9, or that is equals 3 1s are 3, 3 3s are 9, which gives us a remainder of 1 by 3. So this is the p by q form of 0.3 bar. So like this we were able to find the decimal expansion of the non-terminating p by q form of non-terminating decimal expansion. Now let us take another example of this, like question number 3, 1.27 bar. So we have to find the decimal expansion of this number. In the p we have to find the p by q form of this number. So as you can see, two numbers are terminating, so we multiply the decimal expansion by 100, like let us assume x equals 1.27. So as you can see, there are two numbers after decimal expansion. We can write this as 1.27, 27, 27, 27 and so on. So now we multiply by 10 in both sides, so we get 10x equals, so no here as there are two numbers which are recurring, so we multiply the equation by 100, so it gives us 100x equals 127.272727. So now we subtract both the equations and we get 100x minus x equals 127.2727 minus 1.2727. As there are infinitely many numbers after this, so from both sides we can neglect. So 127 minus 1 gives 126, and the decimal expansion after this, the point numbers all get cancelled, and 127 minus 1 gives 126, and 100 minus 1 gives 99x. So from here x equals 126 divided by 99. So here we get 126 by 99. It can be further simplified as 3 3s are 9, 3 3s are 9, so 33, 3 4s are and 3 2s are 42 by 33, and 3 1s are, 3 4s are, 3 11s are. So 14 by 11 is the final value of this. Let's take another example of non-terminating decimal expansion. So let's take an example of 0.235 bar. Here the bar is on 3 and 5. We have to represent this in p by q form. As you know, in the bar there are all two numbers, so we should multiply the equation by 100. So which gives so here we know x equals 0.2353535. So when we multiply the equation by 100, we get 100x equals 23.5353535. When we subtract both the equations, we get 100x minus x equals 23.53535 and so on, minus 0.23535 and so on. So as you can see that the first number after the decimal expansion here is 5 and here is 2, and the second number here is 3 and here also is 3. Third number here is 5 and here is 5. So as you can see that here 35 35 35 35 is repeating, so all the 3 5s will get cancelled with each other when we subtract both, and at last we have to subtract 23.5 and 0.2. So when we subtract both, we get 23.3, and this 100x minus x will be 99x. So when we and we multiply both side by 10 to remove the decimal expansion, so 990x equals 233, and from here we get x equals 233 by 990. Okay, so now let's jump to another type of question. Like now we have to find any 5 irrational numbers between these two numbers. So now I will explain you how to find irrational numbers between any two numbers. So 1 by 7 is a number and 2 by 7 is a number. So first we will divide 1 by 7, which gives us the remainder of 0.142857 bar, and when we divide 2 by 7, we get 0.285714 bar. You can do this by dividing 7 by 1 in a rough page. I will show you of 1 by 7, and of 2 by 7 you do yourself. So as here you can see 1 7. So when we divide, as you know, so 1 is smaller than 7, so 0, 7 1s are 7, 3 30. The closest number to 30 is 28. 7 4s are 28, which gives the remainder 2, and now we have 20. The closest number to 20 is 14, which is 7 2s are, and here we got minus 14, which gives us 6, and 60. The closest number to 60 is 56, which comes 7 8s are, 7 8s are 56, and we get a remainder 4 and 0. And the closest number to 40 is 35, and it is 7 5s are 35. This gives us 5 50. The closest number to it is 7, which is equals to 49. And again we got 1, so the steps will start continuing, so we will get a recurring 1 4 2 8 5 7. So in the same way here also we will get. And now we got the two numbers. Now we have to find three rational numbers between these numbers. So it is very simple. As you know, it is 0.142857 bar, and this second number is 0.285714 bar. So as you can see, the number should be greater than 0.14 and should be smaller than 0.28. So between this number we have to find any three irrational numbers. So one of the irrational number will be 0.15155, 1555, and so on. And the other irrational number may be 0.170, 700, 7000, and so on, like this. And the third irrational number may be 0.20, 200, 2000, and so on. So these are the three irrational numbers between two numbers. To find the irrational numbers between any two numbers, we have to first divide that number and find the decimal expansion of both the numbers, and then we have to take the first two decimal places, and the number which we are taking should be greater than these two numbers and should be smaller than these two numbers. So like this we find the irrational numbers between any two numbers. So now let's come to exercise 1.3, and now here I show you exercise 1.3. As you can see, the first question: write the following in decimal form and say what kind of decimal expansion each has. So here you can see it is 36 by 100. So as you know, when we divide any number by 100, we have to go two decimal points towards the right side. So 36 by 100 equals 0.36, which is a terminating decimal expansion, and it is non-recurring. It is a terminating decimal expansion. So this is the first one. And the second number is 1 by 11. When we divide 1 by 11, 1 and 11, 0.0, and here we get nothing. So again we add another 0, so this is the 9, 0.9, 99, 1. So again this process continuously happens. 0.0909090909 starts on continuously repeating. So here we get 0.09 bar. So it is a non-terminating and recurring decimal expansion. And now we take the third example, which is 4 1 by 8. So here it is a type of mixed fraction, and we have to convert it into analog fraction. So 8 4s are 32 plus 1 33. It comes out to be 33 by 8. So now we divide 33 by 8, 33 and 8. So the closest number to 33 is 4 is 32. So 8 4s are 32. Here we get 1, and as 1 is not divisible by 8, we add a point, and here we add a 0. So 8 1s are 8, which is closest to 10, and 2. So we add another 0. So the closest number to 20 is 16, which is 2 times of 8, 16, and we get 40. And the closest number to 40 is 40 itself, as 5 8s are 40. As you can see, the answer is 4.125, which is terminating decimal expansion. And now let's go to the fourth one. And the fourth one is 3 by 13. And so when we divide 13 by 3, we get this number is smaller than 13, so 0.30. The closest number to it is 26, which is 2 times of 13. We get 4. So the closest number to it is 39, which is 3 times 39. We get 1. The closest number is nothing to it, so we add a 0, and we add another 0 here, as and here 2. So the closest number to this is So the closest number to 100 is 91, which comes at the 13 sevens. 13 sevens is 91, and so here we get a remainder of 9. And as it is a decimal expansion, we add 90, and as we are the closest number to it is 78, and we place so 13 six is 78, and here we get a remainder 12, so 120. So we so 13 nines are equals 117, and here we get a 3. So this is an terminating expansion, as we again got 3, and here we have, so again we will get the same decimal expansion. So here we got 3 by 13 equals 0.230769 bar. So it is a non-terminating and recurring recurring type of decimal expansion. Now let's go to the fifth one, which is 2 by 11, and when we divide 11 by 2 we get so as we know 2 is smaller than 11, so 0.1119. The closest number to 90 is 88, so which is 8 times of 11, 88 2, and again we got 2, so this process will start continuing, so we will get 0.18 bar, which is a non-terminating and then recurring type of decimal expansion. Now let's go to question number 1 6 part, 329 by 400. So let's divide this number, 329 divided by 400. As this number is smaller, we add a point and we get this. So 400, I think that we should multiply it by 8, and 8 zeros are 32. So 3200. So we get a remainder of 90, and as it is a decimal point, we add 0. So 400 into 8 times is 3200, and 400 into 2 times is 800, and we get 100 here, and and we add another 0. So 400 into 2, again into 2 we get 800 once again, and here we get a remainder of 200, and we again add a 0, and 400 into 5 equals 2000, and here we get a terminating decimal expansion 0.8225. And here the question number 1 is complete. So that is all for today. So tomorrow we will do question number 2 3 4 5 6 7 and 8. So thank you. If you like the video, please subscribe and